Although our galaxy is thought to be almost as old as the universe, it is also rife with newly born stars, unlike many parts of the neighboring universe. It contains places like the Carina Nebula, which contains stars hundreds of times as massive as the Sun, and the Orion Nebula, which has produced tens of thousands of stars over the last million years. The high degree of activity in the Milky Way is unusual because there are thought to be 6 times fewer actively star-forming galaxies than galaxies with minimal star formation in the surrounding universe. This is part of a larger picture in which astronomers are learning that the rate at which stars are generated is declining, and they are curious as to why. How do stars develop? Our knowledge of a star's life cycle is primarily derived from studying stars that are born and extinct within the Milky Way. Nebulae, or frigid clouds of gas and dust, are common in most galaxies and are where stars are created. Nebulae have extremely low temperatures, about 10 K or minus 263 degrees Celsius, which are required for hydrogen gas to condense into concentrations high enough to trigger star formation. More gas is drawn in by the clump's gravity, and as it goes inward, it receives energy from the motion. All the motion's energy is transformed to heat when the gas collides with the clump. This cycle keeps going until the temperature reaches thousands of Kelvin and a star can form. The longest stable phase of a star's life, known as the main sequence, is when 2 hydrogen atoms are fused together to form helium, which the star uses to generate radiation and heat. The majority of a galaxy's light is created by this radiation because it keeps an outward pressure that balances the gravitational force from the star's mass. In order to counteract the stronger gravitational pull, more massive stars must burn through their fuel more quickly, but they also shine the brightest and produce the most ultraviolet light. Low-energy infrared radiation is emitted by lower-mass stars, which also have much longer lifetimes and are much fainter. Most galaxies will have a variety of stars with masses ranging from 0.1 to 10 times that of the Sun. The star will reach the end of its life and become a degenerate star after the hydrogen has been consumed. When a star loses its ability to emit radiation, gravitational force takes over and the star's matter collapses into a white dwarf. This process occurs for stars with masses similar to or lower than the Sun. A similar collapse happens in stars bigger than the Sun. The result of this collapse is a core that can fuse heavier elements, commencing with the fusion of helium into carbon. If the star is large enough, this process can go on indefinitely, fusing further layers of elements as heavy as iron. The outer layers collapse as soon as all the fuel in the layers is used up, and they do so swiftly that they bounce back off the core at a speed that is almost equal to the speed of light. A supernova is a name for this sudden expulsion. The material that is expelled is hurled into the surrounding gas and dust, where it helps to seed the formation of new stars. It also leaves behind a neutron star or black hole. The pace of star formation has changed over time. Since its peak, roughly 10 billion years ago, the universe has produced 9 times fewer stars. In a seminal publication released over 10 years ago, our comprehension of how star-forming activity has evolved throughout cosmic time was finally put into words. Data from dozens of investigations with hundreds of thousands of galaxies observed at infrared and UV wavelengths were collated by Piero Madao and Mark Dickinson. It covered all galaxies, from those close to us to those seen in the early universe, some 13 billion years ago. Based on their relative distances, the astronomers divided this sample of galaxies into groups. With this knowledge, they could track changes in the distribution of galaxy brightness over the course of the universe's existence. Additionally, because stars account for the majority of a galaxy's infrared and ultraviolet light, they could use well-established formulae to translate brightness directly into formation rates. These findings supported the notion that star formation in the early universe was extremely poor. Then, as gas in galaxies got more concentrated, star formation accelerated until it peaked between 10 and 11 billion years ago. Star formation has dramatically decreased since that time. It is now around 9 times below the peak value in the local universe. As a result, only a quarter of the stars were expected to have formed in the most recent 6 billion years, whereas around half were thought to have formed in the first 5 billion years following the Big Bang. In general, astronomers think that the availability of cold gas in the universe determines how quickly stars form. This gas becomes concentrated inside galaxies as they start to form, which enables star formation activity to peak. But after that, the gas starts to run out quickly. We start to witness a fall as stars start to die because supernovae scatter the cold gas needed for new star formation and alter its chemistry. However, because galaxies are intricate networks sensitive to a variety of internal and external influences, it is challenging to pinpoint exactly how this gas becomes unusable. Simulations are useful tools for testing various star formation theories and their interactions with other galactic phenomena. They can be used by astronomers to experiment with the parameters of a fictitious universe to test characteristics like the power of a supernova and determine whether it explains our present data. Some scientists are attempting to understand what the universe would resemble if this trend toward decreased star formation persists. They think that the fuel for star formation will essentially diminish once the stelliferous era, this present period of star-forming activity, concludes. The universe would then be ruled by black holes and other degenerate stars as the remaining stars started to perish. The night sky would substantially fade, solar systems would no longer be able to support life as a result of their central stars being significantly colder, and black holes would begin to eat whatever matter was still present, making the universe even colder and more barren. It's depressing and fascinating to think about this hypothetical degenerate era in the future. Thank goodness, it won't happen anytime soon. This, however, is a hypothetical result of the continuing fall in star-forming activity, and there are many other hypotheses for the final conclusion of the universe. We don't fully comprehend dark energy, the force that is forcing the universe to expand at an ever-increasing rate, which is another potential endpoint. Dark energy may become so powerful that it rips apart galaxies, stars, and even matter until nothing is left, a scenario known as the Big Rip, if this trend persists and the universe continues to expand at an accelerating rate. However, if the growth slows or stops, gravity can take over. Everything would begin to pull toward one another, and eventually the entire universe would come to an abrupt end in a big crunch. One variant of this scenario even claims that the collapse might cause a brand new Big Bang and a brand new universe to begin. Leaving these hypothetical scenarios aside, there is still much to discover regarding the precise causes of the decline in star formation and the implications for the cosmos at large. We should be grateful that the universe is getting older, even though the problem is challenging to solve.